Welcome everyone to the 138th meeting of New Directions in Group Theory and Pyramid Categories. Our speaker today is uh, our speaker today is Gustavo Jasso from the University of Cologne, and he'll be talking to us about the Calabi-Yau Auslander-Iyama Correspondence.
Thank you, Radeep, for the introduction. And thank you also for inviting me to speak at this now very long-running seminar. I think for the second time, I believe, at least. So I'm very happy to be back in the seminar. So today I will report on joint work with Fernando Muro from the University of Sevilla. As Radeep already said, I'll report on a result that we call the Calabi-Yau Auslander-Iyama Correspondence, or maybe one could call it the Calabi-Yau derived Auslander-Iyama Correspondence. I need to start maybe a bit strange to say, but by apologizing that I think my talk is going to be rather technical, but I hope nonetheless you can enjoy it. So I will start directly by stating the theorem, and I will later, after that, for some of you, remind you what the things in the theorem are, and for others, maybe you'll know about them for the first time. So for technical reasons, we need to work over a perfect field, for example, a field of characteristic zero or algebraically closed field. This is just to have a good control of bimodules. So this is some technical condition, but you can safely ignore this throughout the talk. And we will also fix a positive integer d that plays a very sort of symbolic role through the talk as a kind of measure of certain dimension. So I'll now state the theorem. So there are actually two theorems in one: Theorem A from our first paper in 2002, and Theorem D from our more recent paper in 2025, both preprints. The first thing I should say is that Theorem A, in the case d equals to 1, is due to Fernando by himself, and the extension to all positive integers d was then obtained in our joint, well, now hopefully long ongoing collaboration. Was the first step in that collaboration. And the statement is that there is a one-to-one correspondence, or a bijective correspondence between, at least in this case, I'll state two classes of mathematical objects. The first class consists of quasi-isomorphism classes of differential graded algebras, let's say A, with the following conditions. So first of all, the zeroth cohomology of A is, of course, an ordinary algebra, and we will ask that this is a finite-dimensional algebra and that it is basic, meaning that when I decompose it as a direct sum of indecomposable projective modules over itself, all of these projective modules that appear with multiplicity exactly 1. So there are no multiple, no indecomposable direct sums which appear to repeat with repeated multiplicity. This is just to simplify the statement so that we can talk about quasi-isomorphisms of DG algebras directly. So this assumption of being basic. Being finite dimensional is on the other hand crucial. And the second condition is that A, as an object of its perfect derived category, so perfect derived category consists of the compact objects of the unbounded derived category of DG algebra, satisfy a certain property, namely that it's what it's called a dz cluster tilting object. I will remind you later what this means, but you should think of A being a suitable kind of generator of a compactly generated triangulated category that in particular is isomorphic to its default shift. So here's where we see for the first time in this condition, the role of this dimension parameter d. Now, there is a third condition. So the third condition is what corresponds to the theorem in green, the theorem D. So I will skip this for a second. So I will first think theorem 8, which is consisting of only the conditions that are written with white pen. So that's the first class of algebras. Yeah. So intuitively, these are finite dimensional algebras which keep cluster tilting, dz cluster tilting objects in their perfect derived category. Now, the second class consist of equivalence classes of pairs, lambda comma I, where lambda is what it's called a twisted D plus 2 periodic algebra. So we see again the parameter D appearing in this definition. So I'm going to tell you what this means. So lambda is again a basic algebra. And I'm going to assume that it's Frobenius equivalently self-injective. This means that lambda is isomorphic to its K-linear dual as a one-sided module. So not as a bimodule, but that will be symmetric. So just a Frobenius algebra. Second, so this is a necessary condition for an algebra to be twisted periodic. The second condition is that the second component of this pair is an invertible bimodule, so tensor invertible bimodule, with the additional property that it should exist a class in the Yoneda extension space of from lambda to I as bimodules in degree D plus 2. So we see again the parameter. And this class can be, well, like every Yoneda class can be represented by an exact sequence of bimodules with D plus 2 middle terms going from lambda to this invertible bimodule I. But I'm going to ask that I can represent it by a sequence in which all middle terms are actually projective. So in particular, eta witnesses an isomorphism in the stable category of bimodules between the D plus second bimodule CCG of lambda, this is of lambda and this invertible bimodule. So this is in stable category of bimodules, okay? And this is the reason for the name twisted periodicity. So lambda is almost periodic, so it goes back to an invertible bimodule because I have assumed that lambda is basic. I can actually write this bimodule as a twisted bimodule by some algebra automorphism of lambda. So after D plus 2 steps of taking CCG, I get back lambda almost as a bimodule, just the multiplication on the right is twisted by some algebra automorphism sigma. And for later use, I just mentioned that one can define now using the bimodule structure on lambda and all the twist by these automorphisms, which now you will notice by some reason this has to do with some conventions appears on the other side. I can consider a certain algebra which is now concentrated in degrees that are multiples of D. And this is by considering all the powers of this bimodule and its inverse. Yeah. So the inverse is given by the twist on the other side or the twist on the same side by -1. Sigma to the -1. So the statement of the theorem is that these two classes of objects are in bijection with each other. And the correspondence from 1 to 2 is the one that is easy to write down. It sends a DG algebra A to the pair consisting of a finite dimensional algebra, so H0 of A, which is basic, that because A is D set cluster tilting will turn out to be Frobenius, as required by condition A here above, and a certain bimodule, namely, well, I can consider the cohomology of A, and every homogeneous component of this cohomology is a bimodule over the degree 0 cohomology, and I pick the -dth cohomology of A as my preferred bimodule to put inside this pair. And moreover, a consequence of all of the above is that for a DG algebra A as in 1, the perfect derived category of A that admits a canonical DG enhancement, in fact, admits a unique one. So this is a theorem that can be interpreted as a theorem of uniqueness of DG enhancements. We will not comment on this anymore during this talk, but maybe interesting for you to know. So what is for us interesting or important about this theorem is that it allows us to relate or to maybe classify, in the maybe very broad sense of the word classify, certain DG algebras with a certain certain properties in terms of a minimal amount of algebraic data that we regard as being much more elementary than the data needed to describe a DG algebra in general. So now let me now review the refinement of this theorem, which is partially the topic of today's talk. So once we have a bijective correspondence between 1 and 2, we can restrict to a subset of the domain, in this case by adding an additional condition, and we can ask, what is this image under this bijective correspondence? And to see whether we can characterize this image and whether it is suitably nice to describe as we would hope maybe from the original correspondence. So in this case, what we will ask is that the n-fold shift of A as a digibimodule is isomorphic in the derived category, so quasi-isomorphic, to its k-linear dual. So it's taking internally in the category of digivector spaces. Yeah? So this is the linear dual. And we ask that this needs to be true. If this is true, then n here needs to be actually a multiple of D. I haven't told you the definition of this at cluster tilting, but this implies that the cohomology of A is concentrated in degrees that are multiples of D. So because the linear dual of A is also concentrated in cohomology in degrees multiples of D, then n needs to be a multiple of D. Such DG algebras are called bimodule right, sorry, this is not a D, right n Calabi-Yau. Okay, so now having made this refinement and restricted to a subset of the domain, what do we find in the codomain? In the codomain, we find the following additional condition. Well, I now look at this graded algebra, which, by the way, if lambda comes from A as here below, this is isomorphic to the cohomology of A as a graded algebra. So this is a different, a concrete way to write this cohomology in terms of the degree 0 part and this invertible bimodule. So for this algebra, I ask the existence of a graded bimodule isomorphism between the n-fold shift of this graded algebra lambda and the dual of this graded algebra lambda for the same integer, and that is a multiple of D. And in addition, I ask that certain obstruction class vanishes. Yeah, so I will explain this a little bit more later in the talk. So there is a certain class that I will remind you of later, or tell you what it is later, which is called the universal Massey product of length D plus 2. This is a certain cohomology class associated to the graded algebra lambda. It essentially depends on the choice of this exact sequence eta above in a certain sense. And thanks to the existence of this graded bimodule isomorphism, one can define a suitable Batalin-Vilkovitsky operator that one can apply to this class. And well, the statement is that if this expression vanishes, then I land exactly in the image of this correspondence after I added condition C. So the existence of phi is expected, it's induced by the existence of such a quasi-isomorphism. Well, I say maybe zigzag of quasi-isomorphisms if you want, but the fact that these two are quasi-isomorphic implies that there must exist such an isomorphism at the level of cohomology, remembering that this turns out to be just the cohomology. But then there is an additional obstruction, namely one needs to control this vanishing condition. Okay? In general, I think now, well, I want to now explain a little bit of the ingredients that go behind the proof of theorem A, written in white pen, and theorem D with the additional modifications in green. And perhaps for those of you that maybe these closer tilting objects are not the main objects of interest, hopefully some of the ingredients that are used in the proof maybe are something of interest to you. And in addition, I would be, very much interested in learning about possible variants of this kind of classification theorem, where I guess I use the word, I use the word classification in a very vague sense, in the sense that these two things, maybe probably each of them impossible to classify, so they're just bijection with each other. So in the sense of giving an actually complete list. But nonetheless, that's what I want to explain. So what are these cluster tilting objects? So I am assuming implicitly that so if I have a DG algebra A, here I'm assuming that, let's assume for simplicity directly, that this is the cohomology is degree-wise finite dimensional. I again always will assume all objects that make sense to be basic. So when I decompose them in direct sum of indecomposables, which is possible in this context thanks to my assumptions, in these decompositions there are no direct indecomposable direct sums with repeated multiplicity. So such a basic DG algebra A is said to be D-set cluster tilting in the sense of Iyama and Yoshino, who define D cluster tilting, and maybe the D-set is inspired by fundamental work of guys Keller-Opperman in this context. If, first of all, A is isomorphic to its default shift in this perfect derived category, and the additive closure of A, which is the smallest subcategory of the perfect derived category containing A, and that which is closed under finite direct sums and direct summands, coincides with the following two subcategories. First of all, it must coincide with the subcategory of all objects X that do not extend A in the derived category in any degree strictly between 0 and D. Yep. And similarly, at the same time, it should coincide with the subcategory of all objects X that are not extended by A in any degree strictly between 0 and D. So this condition might be unusual for those of you that have not thought about this kind of object. For the purposes of this talk, it is enough to think that this is implying that A is a very special kind of generator of the perfect derived category, and therefore of a compact generator of its unbounded derived category. Now, the first thing that one observes is if D equals to 1, these conditions are empty, so they are so this is satisfied by all objects X. So in this case, A is one-set cluster tilting if and only if the additive closure of A is actually equal to the whole perf of A. So every perfect DGA module is a direct summand of a finite direct sum of copies of A. So it's a very strong finiteness condition on the category. But in general, this doesn't need to be the case. That's just now a different characterization of the objects that are controlled by the additive closure of A. The second condition that follows from the definition, the fact that A is inside this category and that is isomorphic to its default shift, is that if A is D-set cluster tilting, then as mentioned before, its cohomology is concentrated in degrees that are multiples of D. And of course, as I also mentioned before, if A is isomorphic, if the n-fold dual, the n-fold shift of A is isomorphic to the dual of A in the derived category of bimodules, then an analogous statement is true for the cohomologies in the category of graded bimodules. Yeah? Now, in order to show, just maybe as a comment, so for the correspondence to make sense, it first of all needs to be well defined. So if I start with an algebra, that's a DG algebra, that is giving a basic D-set cluster tilting object in the sense above, I would like to know whether the pair consisting of the zero cohomology as an algebra and the minus D cohomology as a bimodule over the degree 0 part does satisfy the conditions 2A and 2B in theorem A. So this was observed first essentially by Dugas, but one can also give an alternative proof using work of several other people, Green, Snashel, and Solberg, guys Keller-Opperman, work of Amiot for the case D equals to 1, work of Lin for the general case, and combined with some results of Norihiro Hanihara. So this is to say that, well, there are various ways to prove this, but basically I wanted to say that to some extent, I mean, in the right circles, the relationship between D-set cluster tilting objects and twisted periodic algebras was known. Another thing I want to clarify, which is often the source of confusion, is the role of this bimodule. This bimodule essentially encodes the action of the default suspension in the following sense. If I have my D-set cluster tilting subcategory, object, then I can consider the additive closure of A, and the condition that A is isomorphic to its default shift means the action of the default shift restricts to this subcategory. Now, by the usual Yoneda functor, the additive closure of A is equivalent to the category of finitely generated projective modules over the endomorphism algebra of A in the derived category, which is nothing but the zeroth cohomology of A as an ordinary algebra. And well, along this equivalence, the shift by D induces an equivalence of the right-hand side, which can be identified with the tensor product with the bimodule H to the D, so the dth cohomology of A, which turns out to be invertible with inverse the H to the minus D. So essentially, this is telling me how to I keep track of the zero cohomology and of the action of the default suspension on this category. So that's one role this bimodule plays in this story. So I'll give you now, just as a matter of motivation, very few examples of algebra. So there are many more that you can find in our first paper in the last section of DG algebras A that can be plugged in the class 1 that appears in the original correspondence, and actually many times also, most of the times also in the refined correspondence and the Calabi-Yau correspondence. The first example is just the algebra of Lorentz polynomials in a single variable of degree minus D. That's just a convention. One easily checks that A is a D-set cluster tilting object of its derived category. In this case, the zero cohomology is, of course, K, because this DG algebra has no differential. And one also checks easily this condition. In this case, our result is already known. It's related to the well-known intrinsic formality of Lorentz polynomial algebras. Now, there is another class of algebras or DG algebras that appear in representation theory of finite-dimensional algebras, and these are the so-called D+1 Calabi-Yau completions in the sense of Bernard Keller of D representation finite D hereditary algebras in the sense of Iyama and Opperman. You don't need to know what these are. It's just some interesting class of homologically smooth D+1 Calabi-Yau algebras. And if I take A to be the derived endomorphism algebra of pi viewed in its cosingularity category, so the quotient of the perfect derived category of pi by its so-called perfectly valued derived category. So this is a suitable. So this is the category of DG modules with finite dimensional total cohomology. And thanks to the smoothness assumption, there is such an inclusion so that this quotient is well defined. So this algebra is known to be D-set cluster tilting. Its zero cohomology is what is called the D+1 preprojective algebra of this D representation finite D hereditary algebra, again, in the sense of Iyama and Opperman. And we also have this right D Calabi-Yau property. Examples of this are, for example, if one takes derived two preprojective algebras of ADE quivers, so that H0 of pi is the ordinary Gelfand-Polynomial preprojective algebra. In this case, this fits in the above, and perf A is the stable category of Cohen-Macaulay modules over the corresponding ADE surface singularity. That is the content of Auslander's algebraic version of the Mackay correspondence. And for D equals to 2, one can take the Ginsburg Calabi-Yau DG algebra of a self-injective quiver with potential in the sense of Derksen, Wyman, Selibinsky, and self-injective means that the Jacobian algebra, which is the zero cohomology of pi, is a self-injective finite-dimensional algebra. And in this case, perf of A is the corresponding two Calabi-Yau amio cluster category associated to this QP. Yeah, so there are some classes of DG algebras that, some mathematicians are interested in that fit in this theorem. There is another important class, which are the 2Z periodic derived contraction algebras that arise in the context of the Donovan-Williams conjecture, which was one of the main applications of this theorem that was pointed out to us by Bernard Keller. But I will not speak about this application today because of a lack of time. But maybe you're interested, you can find notes or other talks on this topic by either Bernard Keller, Fernando Muro, or myself, if you want to hear about that. So anyway, so there are some examples. Now we'll forget about that. Now I want to move on to the machinery that enters the proof of the theorem. Now, as it turns out, we're interested in classifying first certain DG algebras, and then afterwards in guaranteeing that certain bimodules or DG bimodules are quasi-isomorphic, namely the n-fold shifted dual of the diagonal of A and its k-linear dual. And already if I look at classifications of algebras, well, one realizes that this is essentially a problem of homotopy theory. So in the background of these constructions, there is a certain amount of homotopy theory and an obstruction theory that is intrinsic to our proof in a way, so to our approach, that might not be that manifest in what I explained today, but I will try to make some hints about this. So how do we proceed? We take a DG algebra that has, well, most of the properties that we would like to have. So something that looks like it could be the derived endomorphism algebra of a D-set cluster tilting object. So, well, it needs to have cohomology concentrated in degrees that are multiples of D. It needs to be locally proper, meaning that its cohomology is degree-wise finite-dimensional. We wanted that its zero cohomology is not just finite-dimensional, but basic, so we add that. And we ask that A is isomorphic to its default shift in the derived category, but this is the same as asking of a degree D for a degree D cohomology class, which is invertible. That invertibility corresponds, of course, to the fact that this map is, the corresponding map here is an isomorphism. So for example, we could have taken A such that we get a basic D-set cluster tilting object, but not quite. So we would like to first understand when is such an A D-set cluster tilting. So to simplify the notation, we will write lambda, also motivated by the notation used in the correspondence. We'll write lambda for the zero cohomology of A, at least sometimes. And this boldface version of lambda, which we call the graded lambda, this is the twisted Lagrange polynomial algebra with coefficients in the degree zero cohomology of A, but where the multiplication is twisted by an automorphism, algebra automorphism given by conjugated by this class. Yeah, so what this buys us is that we can write the cohomology of A as a graded algebra in terms of the zeroth cohomology of A as a twisted Lagrange polynomial algebra. So if you remember, the automorphism sigma is closely related then to the bimodule H minus D of A and to its inverse HD of A. So we are actually trying to depart from the most well understood case of Lagrange polynomial algebras, which are intrinsically formal, by allowing algebras of a more general shape, at least at the cohomological level, which are now twisted Lagrange polynomial algebras. Maybe this is some motivation for some of you. Yeah, but the difference is that the algebras we are interested in general, they're almost never intrinsically formal or formal. So there will always be a DG algebra with differential really that we need in order to capture the property of being D-set cluster tilting. Remember, the cohomology will not be enough. Yeah, so here I already wrote this remark that the minus the homogeneous component of the graded lambda is just the minus the cohomology of A as a bimodule over the degree zero part. Now, the first thing we need to do is, because we already know completely what the cohomology is, so basically what we have remembered from A, because of our assumptions, is essentially equivalent to remembering its cohomology as a graded algebra and a little bit more. So together with this decomposition as a twisted Lagrange polynomial algebra, okay? So it makes sense to involve the theory of minimal A infinity algebra structures on the cohomology of a DG algebra. So we will do that. So we will choose a minimal A infinity algebra model of the cohomology. So I will use the notation M to the A to remember that this is induced by the DG algebra A onto its cohomology. Now, I briefly remind you that this consists of some, operations of arity n degree 2 minus n, for all n bigger or equal to 2. So there is no unary operation, there is no differential because the cohomology of A does not have a natural differential. That's what minimal means. It means M1 of A equals 0. And because the cohomology of A is concentrated in degrees that are multiples of D, the operations of arity I plus 2 that do not vanish need to satisfy that I is a multiple of D. Here I'm using the precise knowledge of the degree of these higher operations. So that means that I can simplify the notation. Well, I can maybe expand, but well, anyway, what it means is that when I think about this minimal algebra, infinity algebra structure, I have my graded algebra, and then higher operations started from md plus 2, m2d plus 2, m3d plus 2, and etc. These are the only possibly non-zero operations that can exist. Now, the d plus 2 operation, which is the first possibly non-trivial higher operation, is is by definition a Hochschild cochain for the graded algebra given by the cohomology of A. It has d plus 2 inputs and degree 2 minus this number, which is minus d. And the A infinity equations that need to be satisfied by any minimal A infinity algebra structure imply that this class is a Hochschild cocycle. Okay? So it vanishes under the Hochschild differential. This is the Hochschild cochain complex. This means that I obtain a well-defined class in Hochschild cohomology by degree d plus 2 comma minus d for this graded algebra lambda. So the Hochschild cohomology now is bigraded because this algebra is now graded. And this is called the universal Massey product of length d plus 2, which in case d equals to 1, was investigated, for example, already by Benson, Krause, and Schwede. And in actually not in a related context, I would say, but it was an invariant that is known relatively classical for d equals to 1, where this number d plus 2 is 3, right? Okay, so we obtain this class, which actually turns out to be an invariant of the quasi-isomorphism type of the DG algebra A. So by passing to the minimal A infinity algebra model, we get access to this additional invariant that seems to be hard to get your hand on if one does not pass to the minimal A infinity algebra structure. Then we consider the inclusion of the degree 0 part of lambda in the graded lambda. This is a graded algebra map. Yeah, it's the inclusion of the degree 0 part. And this induces a restriction map in Hochschild cohomology just by noticing essentially that if I take Hochschild cohomology of lambda with coefficients, so graded lambda with coefficient graded lambda is a bimodule over the degree 0 part. So this essentially gives me this restriction map. And the image of the universal Massey product of length d plus 2 under this restriction map, which is what we call the restricted universal Massey product of length d plus 2. Which under the standard identification of this Hochschild cohomology of this graded algebra concentrated in degree 0 with coefficients in this graded bimodule as the extensions between bimodules, which are now ungraded between the original algebra in degree 0 and the degree minus d part. So this is the degree minus d part of this graded bimodule. We obtain essentially an extension of this by this with d plus 2 middle terms, at least the class of such an extension. So we see that it starts to resemble the condition of twisted periodicity. And we see that, well, for A as above, so that's one important theorem in our work, that A is basic D set closer tilting if and only if the restricted universal Massey product exhibits an isomorphism between, sorry, I don't know what happened here. The d plus second CCG of lambda as a bimodule over itself, and this twisted bimodule, which is an invertible bimodule. So this is telling me that not only that the zero cohomology of A is twisted d plus 2 periodic, but that the witness of this is the restricted universal Massey product. Yeah. So that's the slogan, that the restricted universal massive product witnesses the dz cluster tilting property of the algebra. Okay, so what we should get from this is that the restricted universal massive product and its unrestricted variant, so the universal massive product, are quite fundamental invariants in this story. They allow us to detect the dz cluster tilting property, for example. Yeah. Then we have well, another theorem that I want to tell you about, because so and this is part of the talk, is a reminder on the previous work for those who have been, for example, at this seminar last time I gave a talk, and maybe for others is new, but it's necessary to explain, I think, better what are the novelties in the new paper. So there is another theorem in our previous work called Theorem B, just in case you want to look at the paper, which allows me to determine the quasi-isomorphism class of certain algebras under certain conditions. Okay, so it is similar. So it actually, in specific circumstances, as explained here above, it recovers Kadishvili's intrinsic formality theorem, which allows us to detect intrinsically formal DG algebras. So the theorem says the following. I have a DG algebra whose cohomology is concentrated in degrees that are multiples of D. And I ask that certain cohomology that we call the Hochschild-Massey cohomology associated to this graded algebra here and this invariant vanishes in certain by degrees as prescribed by this range. So in degrees p plus 2 minus p for p bigger than d. So we see again this parameter playing a fundamental role in the discussion. This 2 is marked in red because later I will make another statement where this will transform into a 1, and this is not a mistake. It's just to keep it in mind that there is a difference there, and in fact it's mostly to remind myself of this possible pitfall. I will tell you what this Hochschild-Massey cohomology is in a second. And what the theorem says is that, well, if this vanishing occurs, if B is any other DG algebra with the same cohomology as a graded algebra, and with the same universal massive product, then B is quasi-isomorphic to A. Okay? So as I mentioned, this can be understood as a generalization of Kadishvili's intrinsic formality theorem, which occurs when D equals to 1, and I ask additionally this vanishing. As I will be, hopefully, for those who you don't know this theorem, a bit clear from the discussion below. Yeah, so this theorem is related to the injectivity of the correspondence. Yeah, because this allows me to decide when two DG algebras are quasi-isomorphic. So if I want to use this theorem to say, well, if I send them down through the correspondence, then maybe I can verify all of this. So A and B are already quasi-isomorphic. Yeah, I will not elaborate on that, but that's the role of the theorem in the proof. So here, this Hochschild-Massey cohomology of the theorem is the cohomology of a certain complex whose components are the Hochschild cohomologies of this graded algebra itself. Yeah, so there are the actual Hochschild cohomologies. And the point is now that the universal massive product endows these cohomologies with an additional differential. So normally the cohomology of a complex doesn't have a differential, but this additional class gives me now a differential of by degree d plus 1 minus d. If characteristic is equal to 2 in this by degree, it needs to be given differently. Forget about that. Essentially, it is given by taking a class X to its Gerstenhaber bracket with the universal Massey product. So the Hochschild cohomology is a Gerstenhaber algebra, and I'm using the Lie algebra structure or shifted Lie algebra structure that exists on it. So, for example, the fact that the Hochschild-Massey differential of this complex squares to 0 uses the fact that the Gerstenhaber square of this class is 0, which is true because it comes from a minimal A infinity algebra structure, and if the characteristic is not 2, this is nothing but half of the Gerstenhaber square of that class. So this is an additional quadratic operation that exists in the Gestenhaber, it's part of the Gestenhaber structure on the Hochschild cohomology. So, as a remark, this Hochschild-Massey complex arises as the D plus first page of an extended Bausfield-Kahn spectral sequence that was already studied extensively by Fernando in the case D equals to 1, and actually with little modification, his work extends to the Higher case. So this is to say that this complex should be understood as the obstruction of certain quasi-isomorphism, as containing obstructions for the existence of a quasi-isomorphism between A and B in a suitable sense. Yeah. So I unfortunately have not so much time to talk about this, but I want to say that the definition of this complex is not arbitrary. It is motivated by putting the problem in a certain machinery that gives rise to this extended Bausfield-Kahn spectral sequence. Now, having recalled all of that from our previous work, I want to explain what is novel in the new work that is needed to prove diversion with the additional Calabi-Yau assumption. So what I want to explain now is what are the analogs of the universal Massey product and theorem B, but for DG bimodules over DG algebras. So now we will fix a graded algebra, say lambda graded, for example, the cohomology of a DGA, and M, a graded lambda bimodule, for example, the cohomology of a DG bimodule over a DGA from which this came from. Then there is a certain complex obtained by tensoring M on both sides with the bar resolution of A that computes the bigraded space of self-extensions of M. I have given here explicitly what it is, but what's important is that its cochains are multilinear maps of degree R for all possible R's, where I'm allowed to have P inputs on the left of M and Q inputs on the right, and exactly one input from M in the middle of this P and Q inputs. So you can see how this could have to do with, maybe if you know what's a minimal A infinity bimodule, with A infinity bimodule structures on M, in the same way that the Hochschild cochain complex has something to do, of an algebra, has something to do with A infinity algebra structures on it. Okay? It is endowed with some differential that I don't want to explain, but with this differential, the cohomology of this complex, as I said, computes the bigraded vector space of self-extensions of M as a bimodule. Now, with this, we introduce a new complex that we call the bimodule I try to correct this. Hochschild complex. It is a certain mixture of the Hochschild cochain complex for lambda and this this bimodule complex for M that computes self-extensions of M as a bimodule. In fact, this is given explicitly as the standard cocone of a natural map from the Hochschild cohomology of lambda to this other complex that I stated before, which uses the fact that this complex here is naturally a bimodule over the Hochschild cochain complex of lambda. I also don't give the formulas for lack of time, but you can find them in our paper called the Calabi-Yau, the derived Auslander-Iyama Correspondence 2. You can find there all the formulas with care. So we will define this complex as this cocone. So here I already have my preferred differential, so I only need to tell you what is the map. So here, of course, I just explained the cocone is given by this complex plus the shift bind -1 of that complex. And it has the differential, which is given by the differential of the cocone, where I need to negate the differential of this. That's the reason for having this convention here of the sign. And the connecting map gives, of course, the missing lower entry in the differential, and it's given by essentially the commutator of the action of a cochain coming from here with the identity of M, which is an element of here in degree 0, 0, 0, 0, right? So it has 0 inputs on the right and 0 inputs on the left, exactly 1 input from M in the middle, and has degree 0. So yeah, so this is a very natural map to consider. Is really the commutator of the left and right action of this complex on this specific element. And the cohomology of this complex is what we call the bimodule Hochschild cohomology of the pair lambda. This is also a Gerstenhaber algebra. The reason for this is, well, if you know one way to construct the Hochschild-Kochen complex as coming using the brace operations obtained from the endomorphism operand of this graded algebra, you can apply the same construction to the linear endomorphism algebra of this guy to get this complex, where one uses the multiplication of the square zero extension. So here one uses the multiplication of the algebra, and here one uses also the multiplication of the square zero extension. So it's for formal reasons. This is also a Gerstenhaber algebra, but this is extremely important. And as also a side remark, by construction, there is a triangle of bigraded vector spaces that relates this new cohomology theory with the Hochschild cohomology of lambda and the extensions, self-extensions of M as a bimodule. Yeah, this is because we define it as a cocoon. Okay. So what do we want to do with this? Well, we want to now apply this to the case where lambda is the cohomology of a DG algebra whose cohomology is concentrated in multiples of D. And instead of M, we will consider the cohomology of a DG bimodule over that algebra whose cohomology is also concentrated in degrees that are multiples of D. For example, M could be the dual of the diagonal, they'll satisfy this condition, or could be the shift of the diagonal by a multiple of D. They'll also satisfy this condition. And of course, these are the two bimodules that we're interested in comparing when we want to know when they are quasi-isomorphic, right? This is the missing condition, put in green, condition C, in the Calabi-Yau Auslander-Iyama correspondence. So for this, what we now do is we do as before, we choose a minimal A infinity algebra model for the algebra A, and a compatible minimal A infinity bimodule model for M. So meaning that I want now to give the cohomology of M the structure of a minimal A infinity bimodule over this minimal A infinity algebra. Such a structure is given by a collection of operations, like depicted below, where I need to consider all possible ways to multiply. I have P inputs on the right coming from the cohomology of A, Q inputs, sorry, that's the left, Q inputs on the right coming from the cohomology of A, one input in the middle from the cohomology of M, with output the cohomology of M and the suitable degree as before. So we see just by their shape, and they need to satisfy some equations, A infinity, bimodule equations. But what we see is that if I take the sum of these guys, they live in this complex, right? Which contains a part which is looking like the Hochschild cohomology of A, coming from this, Hochschild-Kochen complex of A coming from this part, and these kind of operations that we saw come from this other complex that we would have denoted in this case like this. Actually, that's not an A, that's the graded lambda. Okay, so we can form a new cochain, and just as before, by the degrees in which these cohomologies are concentrated, the only operations that can be possibly non-zero are the ones of arity I plus 2, where I is a multiple of D. And just also as before, one can check using the A infinity bimodule equations that this new class, also in the same D plus 2 degree as before, is a cocycle in this new complex. This means that we get again an invariant now of the pair algebra and bimodule, so of this pair, which we call the bimodule universal Massey product of length D plus 2, because I suppose we're not that creative. So this is, I actually much prefer very explicit names so that I remember what things are and I don't get confused. So yeah, we call it the bimodule universal Massey product of length d plus 2. And I mentioned that this is also a Gerstenhaber algebra. And it turns out also that the Gerstenhaber square of this class also vanishes. So one can define again a complex. So there are two complexes that one could define at least, but in this case we now focus on one, which we call the bimodule Massey complex. The name didn't survive here, so this is the bimodule. I think I moved this and might be here on the bottom, bimodule Massey complex. And this bimodule Massey complex is now associated, well, it depends on this bimodule, this graded algebra, and this bimodule universal Massey product. Its components are given by these extension spaces of this cohomology as a bimodule over the cohomology of A. And it has a differential given again by the Gerstenhaber bracket with this bimodule universal Massey product. And the resultant cohomology, we call it the bimodule Massey cohomology. Now we have a way to state a version of theorem B for bimodules. So if I have a DG algebra A and a DG A bimodule over A, both of which have their cohomology concentrated in degrees that are multiples of D, then I can ask whether this new bimodule Massey cohomology vanishes in a suitable by degree, where now here's the number 1 that I mentioned that in a different theorem it was a 2, but now here it is a 1. And I ask it vanishes in a suitable range. Then in this case, if I have any other DGA bimodule whose cohomology is isomorphic to the cohomology of N as a bimodule, and the class of this difference vanishes in this extension space, so this is where this class turns out to live, then N is quasi-isomorphic to M. Yeah, so again, we have a theorem where we now think, okay, if I could take, for example, M to be the dual of the diagonal, or M to be the n-fold shift of the diagonal, maybe if I could verify this, then these two bimodules will be isomorphic, and this is precisely the right bimodule N Calabi-Yau property, or bimodule right N Calabi-Yau property. So that's now the role of this theorem. So in order to apply this, what do we do? So I haven't told you what's the Batalin-Bilkovitsky operator, so this will be the very last thing I will do. So first of all, well, if I have a DG algebra whose cohomology is concentrated in degrees that are multiples of D, and I assume that at the cohomological level, I have this bimodule N Calabi-Yau property at least, then the class that appears in the theorem B for bimodules is 0 in the correct space, if and only if the Batalin-Bilkovitsky operator associated to phi that I haven't told you about applied to the universal Massey product of A as an algebra. So this is the part of the universal Massey product of A as a bimodule. Here is as an algebra. This vanishes. So I can change the vanishing that appears in theorem B to a vanishing that appears that talks only about the algebra universal Massey product. Yeah, so I don't need to look at the bimodal universal Massey product, but at the algebra universal Massey product. But I need to use the Batalin-Bilkovitsky operator. So in order to use this equivalent vanishing statements, one observes that if I have a graded algebra, then there exists an isomorphism between this new bimodule Massey, Hochschild-Massey cohomology, and the cohomology, the Hochschild cohomology of lambda, but now dual numbers in a variable of degree 1,0. So that has to do with the vanishing of the connecting homomorphism at the cohomological level, using the fact that the Hochschild cohomology is graded commutative, and delta was sort of measuring the difference between the left and the right action of the algebra, and in fact is related to whether a module is symmetric or not. So in this case, one gets this result. So if our lambda comes from the cohomology of a DG algebra concentrated in degrees that are multiples of D, then kappa, this isomorphism, sends the class we're interested in to essentially the class, well, this Batalin-Vilkovitsky operator applied to this other universal Massey product as an algebra. So here we see, because it's an isomorphism, that this is zero if and only if this is zero. Okay. Now, to conclude, I want to explain what I wrote here. So this is the difference between the bimodule universal Massey product of the diagonal concentrated in degree 0, and here I have the dual of the diagonal shifted in degree minus n. Yeah, so you should think that I try to, I mean, if I have such an isomorphism, I can change it to such an isomorphism, right? So I can, if I have this quasi-isomorphism, I can have this, so I can kind of normalize the situation in this way. And in fact, this guy here, well, it actually doesn't live in the same graded vector space H star of A, yeah, which is where this lives. I need to use the identification between the dual of the diagonal and this, or equivalently this and the dual of the diagonal shifted by n, which is the same as the dual minus n, which is the same as this. So I need to sort of transport the minimal A infinity algebra structure to the same graded vector space. And well, one can do this. So there is there are explicit constructions at the level of this cochain complex that translate, for example, the minimal A infinity structure on the diagonal to the minimal A infinity structure that is induced on the shifted diagonal. And then you can explicitly translate the minimal A infinity structure on the shifted diagonal to the minimal A infinity structure that you are supposed to get on the dual of the shifted diagonal. And then using such an identification, you can translate this into a minimal A infinity structure that lives on top of this graded vector space. Again, so that you can really make the comparison. Okay, that's the first thing. And then in the last minute, I just tell you what is this Batalin-Vilkovitsky operator. So this comes directly out from the computation of this composition. And it turns out to be just an n-shifted variant of the classical Batalin-Vilkovitsky operator that is constructed for more typically in the case n equals to 0. So given this map, I can consider the induced pairing on shifted vectors. So I use this to denote shifted elements of this graded vector space. It's just the usual induced pairing. And the Batalin-Vilkovitsky operator is just you characterize by the following equation in terms of this non-degenerate pairing. Okay, so this is for those of you who know about that. That's how it arises. It arises by understanding what you need to do to transport the minimal A infinity algebra structure from the diagonal to the dual of the shift to the diagonal and back to the diagonal along such identification, and understanding the image of this obstruction class under kappa. So that's how this thing arises. Yeah, thank you very much. So that's all I had to say. Thank you for your attention.
Thank you, Gustavo. Let's give the speaker a round of applause. Okay, if you have any questions for the speaker, ask them now.
So I have one question at page 2 when you give this example about this higher pre-projective algebra. So I guess it it is defined as this zero homology, right? Of some.
Yes. Well, that's a possible definition. Yes.
Yeah. So here's the question: is there a way to reverse that thing? So if we start with a given higher pre-projective algebra, is it possible to construct this algebra A, the differential graded algebra?
Well, yes, in a way, this is essentially part of the content of the correspondence. So this is this guy here is your lambda, right?
Yes.
And the only thing that you need to know is what is the minus d cohomology of this, right?
Mm-hmm.
But for that, what you need to use is that in this case that you have this isomorphism to the shift, so you can use that to recover it. And then there is a non-constructive procedure to recover the DG algebra A. I didn't explain anything about the surjectivity of the correspondence.
Mm-hmm.
So this is surjectivity means a preimage exists, right?
Okay.
And we exhibit, we prove that such a preimage exists, but there is no clear, algorithmic procedure to produce it. This deduced by a successive vanishing of obstructions that allow you to promote the cohomology. So what I'm trying to say is that in the context you're interested in, you more or less know basically the cohomology of pi as a graded algebra. Yeah, that's essentially the question from where you start.
Yes.
The problem is now, because you can recover the sigma using the Nakayama permutation of this guy and so on. Yeah? It's because it is now in the D Calabi-Yau case, you can use Nakayama permutation to get the twist and so on. So you know basically this. The question is how to promote this to a minimally infinity algebra structure whose universal Massey product gives you the twisted periodicity. And this is like a successive, you construct the operation sort of in steps, and you argue that they can be extended and so on, but it's not so constructive.
Okay, I see. Thank you.
Thank you, Amra. Any other questions? Here's a I don't know, meta question, Gustavo. Are there any conjectures other than the Donovan-Weems conjecture that could now be killed with the newer conclusions?
I don't know. I definitely, unfortunately, don't know. The algebras that appear, so the 2Z periodic contraction algebras, derived contraction algebras that appear as in the context of the Donovan-Weems conjecture are two Calabi-Yau. So they're appearing in a two cluster categories, in a two Calabi-Yau cluster category. That is even two periodic. Yeah, so there is a singularity category that can be described as matrix factorizations. But this additional information maybe plays a role in the proofs, maybe in some other statements. The Calabi-Yau assumption, it is used, for example, to show that the ordinary contraction algebras are symmetric, for example. It involves this, but not in the part that our theorem contributes to. And as far as I remember, I might be wrong about this, also not so explicitly in the new proof by Joe Karmazin, Emma Lepre, and Michael Wims. So it's not so clear. So in this case, we really, what a possible application for this is to deduce the bimodule Calabi-Yau property in a context where you don't have a clear strategy of how to prove it. But in fact, nowadays, one knows that there are more interesting. There is such a thing called a genuine, or maybe not genuine, but just like a right in Calabi-Yau structure. So one would like to have a condition on when such a right Calabi-Yau structure exists that induces the bimodule isomorphism that you need. And this is maybe the subject of different work. So we are after trying to guarantee when such genuine right Calabi-Yau structures exist automatically. For example, so that we could apply the relatively recent theorem of Keller and Liu on the modified Amiot conjecture, characterizing cluster categories of quivers with potentials, at least in the Jacobi finite case, because in their theorem, a crucial modification to the original conjecture is the existence of a right Calabi-Yau structure on the enhancement. So we would like to know whether in some cases it automatically exists, but we do not know this at this moment. So this is still, maybe this is the next frontier for us in this particular project.
And the work of Sondre and Martin Herschel and others, like where they give like classifications of NZ cluster tilting subcategories of like honest module categories. Is there any relationship between those kind of questions and
Yeah, so there are now a few papers where people have constructed some NZ cluster tilting or DZ cluster tilting subcategories or objects in some triangulated categories. And yes, of course, all of those fit in this correspondence. So what I would be, so this tells us, for example, that those triangulated categories have unique DG enhancements and things like this. But what I guess one would also like to have in general is maybe an understanding when one has a twisted D+2 periodic algebra, whether the DG algebra that exists because of the theorem has a nice alternative realization or interpretation. Yeah, this is maybe the direction that seems to be also interesting.
Okay.
Mhm.
Okay, thank you. Any other questions, anybody? Oh, Bernard is here. Okay, didn't see him. Okay. Okay, if we don't have any more questions, let's thank Gustavo once again.
Thank you.
We have Marina Godino next week.